Black Friday, 10,000 orders flooding in. Your dashboard shows numbers, but you have no idea if you're winning or losing. Staring at a spreadsheet tells you nothing. You need to see the pattern. Where's the money actually coming from? What's normal? Where are the outliers? That's what we're covering today. Data distributions. This is the skill that separates people who report numbers from people who make million-dollar decisions. By the end of this video, you'll read data the way executives and senior analysts do, like a story with clear heroes, villains, and plot twists. We're going from raw histograms to the bell curve to advanced concepts. No fluff, just what you need to sound like you've been doing this for years. Let's go. So what exactly is a distribution? Look at the definition on screen. A distribution describes how data points are spread across all possible values in a dataset. It tells us how often each value occurs. Think of it like this. You're not just asking, what's the average? You're asking, where does most of my data actually live? Real-world example on the slide. Collecting test scores from a class of students. Scores go from 2, 4, 5, all the way to 30. By counting how many students got each score, you can visualize the shape of the class performance. Look at the histogram on the right. See that peak between 11 and 15? That's where most students landed. The small bars, those are your outliers. This shape tells you everything an average hides. Are students clustered, spread out, bombing, or crushing it? Here's lightest matters in business. You're analyzing user behavior on your app. Most sessions are 2 minutes. A few hit 30 minutes. If you only look at the average, maybe 8 minutes, you miss the fact that you have 2 completely different user types. The shape reveals segments. The average erases them. Quick question. Think about your daily screen time. Is it consistent, or do you have one massive spike on weekends? Most real-world data isn't flat. It has a shape, and that shape tells the story. Look at the visual. This is the bell curve, also called the Gaussian distribution. Notice how it's perfectly symmetric. The left side is a mirror image of the right side. 3 key features: symmetric shape, perfect balance, no bias to either side. Unimodal, one peak. There's one clear center where most of the data lives. Asymptotic tails, the edges stretch out forever, getting closer to zero but never actually touching. Extreme values are always possible, just incredibly rare. That dashed line in the center? That's the mean, mu, the highest point of the curve, where the majority of data points cluster. Why does this matter? Because tons of real-world phenomena follow this pattern. Heights, test scores, measurement errors, manufacturing tolerances, even response times and customer service. When you see the shape in your data, you immediately know most values are near the center, extremes are rare, and the distribution is balanced. That predictability lets you make confident decisions. Wait, don't get scared. Trust me, complete this video. You will master distribution. The normal distribution has 3 specific properties that make it incredibly powerful for analysis. See that perfect bell shape with the center line labeled mean equals median equals mode? And the 50% split on either side? Property 1, perfect symmetry. The left side is an exact mirror image of the right side. This means there's no skew, no bias. Data is perfectly balanced around the center. Property 2, center alignment. The mean, median, and mode are all at the exact same point. This is rare in real-world data, but when it happens, it tells you one number perfectly describes the center. No distortion from outliers. Property 3, equal split. Exactly 50% of the data falls below the mean and 50% falls above. One warning. Just because mean equals median equals mode doesn't prove your data is normal. Always verify the shape visually first. This is one of the most powerful shortcuts in data analysis. 68%, 95%, 99.7%. This is the empirical rule. It tells you exactly how data spreads in a normal distribution using standard deviations. Look at the visual. See those three zones? 68% falls within one standard deviation of the mean, that dark blue center zone. This is normal behavior. Most of your data lives here. 95% falls within two standard deviations, that wider zone. This covers almost everyone. Anything outside this is getting unusual. 99.7% falls within three standard deviations, the full wide zone. If something falls outside three standard deviations, it's a legitimate outlier. Less than 0.3% chance of happening randomly. Real application. Website load times. Mean is 2 seconds. Standard deviation is 0.5 seconds. Your PM asks, what percentage of users experience slow loads over 3 seconds? 3 seconds is 2 standard deviations above the mean. Using the rule, 95% of users are within 2 SD, so about 2.5% experience loads over 3 seconds. You just diagnosed the problem in 10 seconds. This rule isn't just descriptive, it's for setting thresholds. Quality control, flag defects at 3 SD. Fraud detection, investigate transactions beyond 2 SD. A/B testing, results 2 plus SD apart equals statistically significant. Here's a concept that changes everything. In a normal distribution, probability equals area. Look at the visual. The entire shaded region under the curve equals 1, or 100%. That's the complete probability space. The slide shows 3 mathematical concepts. Total area, 1. Everything that can possibly happen lives under this curve. Area equals probability. The probability of an event falling within a specific range is the area under the curve for that interval. Asymptotic tails. The tails get closer to the x-axis forever, but never technically touch it. Let's apply this. Daily revenue is normally distributed. Mean, $50,000. Standard deviation, $10,000. CFO asks, what's the probability tomorrow's revenue falls between 40K and 60K? That range is exactly 1 standard deviation on each side. From the empirical rule, 68% of the area falls there. So there's a 68% probability tomorrow's revenue lands in that zone. You just did forecasting in 10 seconds using area. When you think in terms of area, you stop treating data as static numbers. You start thinking in probability zones. That's what professionals do. 2 numbers define the entire shape of a normal distribution, mean and standard deviation. Mean, position, shifts the curve left or right along the axis. The shape stays exactly the same. Think of it like sliding a mountain. The mountain doesn't change shape, it just relocates. Increase the mean, curve slides right. Decrease it, slides left. Standard deviation, spread. The standard deviation changes the height and width. Small sigma equals tall/narrow. Large sigma equals short/wide. Look at the right visual. The tall, narrow curve, small standard deviation. Data is tightly clustered, consistent, predictable. The short, wide curve, large standard deviation. Data is spread out, variable, unpredictable. Real example. 2 subscription customers, both average $100 a month. Customer A, standard deviation $5, pays $95, $102, $98, super consistent. Customer B, standard deviation $40, pays $60 one month, $140 the next, all over the place. Which customer is more valuable? Customer A. Predictability reduces risk. You can forecast, plan, budget. Customer B's volatility kills financial planning. Mean tells you how much. Standard deviation tells you how reliable that amount is. The tail tells the tale. Skewness measures asymmetry, whether your data has a long tail stretching in one direction. Right skewed, positive skew. The tail extends to the right. Notice the order at the bottom. Mode, median, mean. The tail extends to the right. The mean is pulled to the right by outliers. High-value outliers drag your average up. Most data is on the left, low values, but a few extreme cases on the right pull the mean away from where most people actually are. Left skewed, negative skew. Tail extends to the left. Order reverses, mean, median, mode. The tail extends to the left. The mean is pulled to the left by outliers. Low-value outliers drag the average down. Real example, mobile game, player spending. Most players, $0 to $5. A few, $10 to $20. One whale, $5,000. You calculate the average, $45 per player. Does $45 represent your typical player? No. The distribution is right skewed. Mode is 0. Median might be $1, but mean is 55 because of that whale. Report the mean to your CEO? You'll make terrible decisions. Overspend on acquisition, design features for a customer who doesn't exist. In skewed distributions, median is king. It shows the actual typical value. The tail tells the tail. Whichever direction the tail points, that's where your outliers live and where your mean is getting pulled. See skew? Investigate the tail. That's where the money, or the risk, lives. Let's lock in the 3 big ideas. Spread and shape distributions describe how data is spread. The normal Gaussian distribution is perfectly symmetric. When you see this bell shape, you know you're dealing with balanced, predictable behavior. The 2 parameters, mean defines the center and standard deviation defines the width spread. 2 numbers. That's it. They define the entire distribution. Change the mean, the curve moves. Change the standard deviation, the curve reshapes. Crucial rules. Remember the 68-95-99.7 rule for probability, and that the tail tells the tail for skewness. 68, 95, 99.7 gives you instant probability calculations. The tail tells the tail shows you where outliers pull your mean and where the real story lives. Master these 3 concepts, you stop reacting to individual numbers. You start seeing patterns, risks, and opportunities in the shape of data. You'll know when an average is lying, when variability is the real problem, when outliers are driving the entire story. If this clicked, hit that like button. Subscribe for more content that teaches professional thinking, not textbook theory. This is the difference between students and professionals. Let's go!